All right, hi everyone. Getting started today with my live stream. Welcome to Primitive Computing. So I guess tonight we're gonna spend some time doing some coding, doing some like boot sector assembly language on for IBM PCs. But first, I'm going to talk a little bit about what I hope to do with this project. So part of it is I'm looking to experiment with doing some coding and sharing stuff with the internet, sharing some knowledge and all of that, but also asking a question about. So I've always wondered like what would happen if we just start from scratch and like start the whole software stack from scratch. And so that's what I wanted to do with this project. So we're going to start out with just an assembler and build hopefully like a whole system from there. So I'm going to be doing like I said, tonight we're going to be mostly looking at the boot sector and playing around with that, having some fun in there. And then, you know, uh, hopefully building, so we want to not just program in assembly language the whole time. So we'll create our own programming language. And then from there, use that to build what looks more like a proper operating system. So anyway, those are the goals that I had for this. And let's get into it. Why don't we just dive into some code? So, yeah, I want to play with the boot sector. The way let's see, where to start with that? Well, I guess let's start with a new file. So I'm going to go ahead and save this as boot.asm, and this is where we're going to start writing things in there. And so I'm targeting the like sort of mid 80s IBM PC. There's a couple of reasons for that. When I was thinking about how do I want to do this project, I thought about, well, like we could go back further. We could build our own computer from chip. We could build our own chips out of sand. We could, where do we start with? And I thought that starting with kind of where the PC world was and like kind of the late 80s is a good spot. And there's a couple of reasons for that. One is it's what most of us are using, or most of us have grown up with anyways, computers that are sort of that style. So like I think a lot of this will be applicable. And then it's also it's very well documented. There have been so many people who've done written so much code or so much software for this environment. And so that means there's a lot of documentation available for it. It's a lot easier for us to pick up and go. The IBM PC BIOS is very powerful, and in some ways it's like kind of almost an operating system itself. But one nice thing is that it was from an era when people still wrote assembly language. It would still be kind of normal to write an entire program in assembly language, and that means it's a lot easier to understand, or it's there's less that you have to like understand and internalize. You don't need as much extra tooling to build it. This is in contrast to like nowadays a lot of systems use UEFI, so like universal extensible firmware interface, and that is very powerful. Excuse me, but it also requires a really you need a whole other computer to bootstrap from. You want like a functional like C compiler or C++ compiler. You want all the libraries. You need to sort of build all that in Flash and like flash your or whatever, save it to a file system and all of that. And I really want to be able to sort of peel back all of that and just see as close as we can what does it look like back at the beginning. So anyway, those are my thoughts and my reasons for starting where we're starting. But let's start writing some code. Let's do that. So while we're doing this, I'm going to be I've got my where's my web browser? There you go. I've got my web browser here. I'm going to be looking up a lot of information on there because I don't really remember a lot of this, and so you'll get to see kind of my research process for this as well. There's a couple of sites that are really helpful. So one's Wikipedia, actually. Like I've gotten a lot of information out of that. And then another one that we're going to be relying on pretty heavily is called Ralph Brown's interrupt list. And this is a list that I don't know how far back it goes. I think it's like back to the like 90s or like early 90s, late 80s. But it lists basically every known like interrupt or BIOS call, and documents it and stuff. So we'll be relying on this pretty heavily as well. And then I think we'll just use some other resources as we go. So there's a couple of things about the boot sector. Basically the way this works is the boot sector is the first sector on your disk. So we're going to pretend that we're using a floppy disk. I'm going to be doing this in a what do you call it? Oh, QEMU. I'm going to be using an emulator to do this. So we will have, we're going to write a boot or a disk. We're going to put our code on the disk, a virtual disk, and go from there. So a basically what the BIOS does for the boot up process is, well, I guess let's go back to the CPU itself. So basically every CPU, when it powers on, it's got to start running a program from somewhere. And that gets, basically it expects that to be hardwired into a certain location in memory. So on PC compatible computers, that's basically where the BIOS goes. So the CPU starts up, it starts running the BIOS. And then the BIOS goes and talks to the disk, the hard drive, the floppy disk, or whatever, and it goes and finds something to use as its boot sector. So disks are broken up into 512 byte sectors, and the boot sector is just the first one. And so basically the BIOS goes and it loads that up and it transfers control into it, and then that gets to take over loading the rest of the operating system or whatever you want. So we have basically 512 bytes of code that we can play with for tonight. So it turns out you can actually do kind of a lot in that amount of space. So let's see, a couple of things we need to do. So one of the things here is it says that the BIOS loads, like I was just telling you, it loads the first sector into memory. But the important thing is to know where it gets loaded into it. And so on Wikipedia here, it says that it loads to the address 7C00 in hex. So we need to tell, our assembler that we're going to be loaded into that same location. So we do that using this directive called org. And we do 0x7C00. Okay. What that says is then everything we write from this point will, it's assuming that this is the location this code is going to be loaded into, and so everything's going to be relative to that address. Okay. So the next thing we do then is like write code. Okay. Anytime I'm getting started with a new thing, to me the simplest program you can write is an infinite loop. So that's what I'm going to write. We're going to start with an infinite loop and see if that works. Okay. So let me open up my terminal down here. Also, let me make the font a little bit bigger. I meant to do that. There we go. That looks a little bit better, I think. One more time. Yeah, let's do that. Okay, cool. So down here in my terminal, I'm going to be using the assembler NASM. It's the NetWide assembler. Not really any particular reason. There's a lot of different assemblers you can use. I like this one because it has sort of like Intel syntax by default or something pretty close to it. And honestly, when I first started writing assembly language, this was the one that I started using. So that's kind of my preference for it. It's nice and simple. So in this case, we can just do NASM boot.nasm. And by default, NASM compiles into a raw binary file, which just means like all it is, just it writes the instructions out there. There's no executable file format around it. So you can't really load this with an operating system, but the code's all there. So, then we have a file that's 2 bytes long. So that's basically a single instruction. We can, let's see. Yeah, in disasm, we can actually look inside it and make sure it compiled the way that we wanted it to. And yeah, so it just assembles it. It says we just basically jump back to the same instruction that we were just on. So that's cool. That's kind of what we wanted, right? Okay, and now we want to try and run this. So like I said, I'm going to use QEMU. Was that system x86-64? Sure, why not? We could use the i386 one too, but it doesn't matter because Intel CPUs kind of recapitulate their entire history for backwards compatibility. So they boot up like they're an Intel 8086, and then you kind of jump through all the different modes from there. Interestingly, I found out recently that the Super Nintendo processor is the same thing. It actually boots up and it's running in the same mode as basically the same processor that was in the NES, and then they have to switch into the 16-bit mode for the Super Nintendo, which I thought was kind of cool. Anyway, if I just run QEMU with nothing, no arguments on there, we get this machine, or we get this, so it's, can I make this bigger? Yeah, here we go. Let me make this a little bit bigger once again. I could just use the, there we go. That's a good size. That pretty well fills, whoops, pretty well fills the screen. Okay, so it booted. It's searching for the floppy. It's searching through the CD, DVD, ROM drive. It tries to do a network boot. It's not able to find any information or anything to boot from. So it's going to refuse to boot. So let's try and give it our boot sector that we just ran into, or that we just created. So what we're going to do is pass the argument FDA, which says here's a file that we want you to treat as the floppy disk image. And so we run this, and let's make that larger again. And the same thing happened. So what went wrong there? Well, fortunately, I tried this the other night, and so I know what problem this is. I did this on purpose, so now we can fix it. So this was I don't know if any of you saw on the Wikipedia page when I was there. There's a section about how it can recognize a bootable partition. And basically it looks for 2 magic bytes in the boot sector. And so it says here it looks for a 2-byte hexadecimal sequence 0x55 0xAA. It's called the boot sector signature at the end of the boot sector. So yeah, anyway, at the end of the, right. So we need those 2 bytes on there basically. And sorry, I got distracted because YouTube's complaining about something. Let me see what they're doing. Yeah, it looks like we're not getting enough video in here, so that's unfortunate. Let me check and make sure I'm not like overloading my computer. Whoops. I'm gonna pull that up there. Oh yeah, I'm using a lot of CPU, but it should be fine. So we'll just keep going. Hopefully it's okay. All right, cool. Well, thanks everyone for putting up with that. I hope, I don't know, maybe someone in the chat wants to say if the stream looks okay. Otherwise I'll quit worrying about it. So anyway, let's get back to this. We want to make this actually be bootable. And so what we're going to do then is we're gonna create a new section. Oops, cannot type. So we'll just call this dot, boot signature. And let me go pull up the NASM documentation also. So it's nasm.us. And docs. HTML format. And let's see. So there's basically what I'm going to do is create a new section here and give it a specific location to start, and that'll basically cause NASM to stick these 2 bytes where we want it to go. So that's going to be, we use the start thing right there. So we'll say boot signature start equals, and then for this one we're going to do we have to do it relative to the origin to make sure that works out well. And since I don't like doing hexadecimal math in my head, I'm going to cheat and do some addition here. So we do 510 bytes off from the end. And then we're going to do 2 bytes. And what did I say that was? I think it's 55 and AA. Yeah. So do 0x55, 0xAA. Do it like that. And so nasm boot.asm again. And now, now we notice our boot file is 512 bytes long, and so that's great. That's a that is the size of a 1 sector, so that's great. We want our boot sector to be 1 sector long. And let's see what happens if we run qemu now. If we're lucky, it will work. If not, you get to watch me troubleshoot. Great. This is what it's supposed to do. It looks like it's not working, I know, but what's going on there is it went through its like boot up process. It says, okay, it couldn't boot from the hard disk, so now it's going to try booting from a floppy. And since our floppy was just an infinite loop, we didn't see anything else happen after that. So cool. There we go. That's pretty awesome. Excuse me. So cool. We now have a working, a bootable program. Let me lose my grab there. Okay. So now let's make it do something a little more interesting. I think what I'm gonna try and do is let's try and make a small game. Boot sector games are kind of fun, and that's a good way to have fun in this. So let's see if we can make maybe a really simple Pong game. Okay, so we can get into a little bit more of what's going on with that. So again, you know, like I said, the BIOS has a lot of functionality built into it. Like it has some decent like graphics and display capabilities. It has some you know, has like functions for accessing the disk and accessing your keyboard and just kind of everything we need. So I'm going to look at using the BIOS to basically we're going to use a lot of that to be able to keep this as small as compacted or as small and compact as possible. Let's try and get some graphics first. That's a good place to start. So like I said in Ralph Brown's interrupt list, there's just a list of a bunch of interrupts. These are things that the BIOS provides. And maybe let's make that a little bit bigger. Yeah, video. Here we go. Let's look at our video. And I wish I could just like make this stay at the larger size, but whatever. Excuse me. Let me drink some water so I don't cough so much. Okay, so we want to set the video mode, and so we're going to use this one, set video mode. It's pretty simple. It's you do it's interrupt 10, and so the way these interrupts work is there's an instruction, the interrupt instruction or INT, which basically can do like, so in you know the BIOS and doing like real mode DOS programming. It's basically this like table of functions, almost kind of like system calls, like on Linux, I guess, where you can cause the CPU to transfer code over to there and you know run. It does provide some services, and then it has this like well-defined interface. So here it says if you want to set the video mode, you set the AH register to 0. And then you choose which video mode you want. And it says if you scroll down, you can see a whole bunch of the video modes that they have. I find this table kind of tricky to read. So anyway, I'm not going to spend too much time looking at it, but I'm going to set the video mode to, it's called mode 13H. I guess that's 19 in decimal. And the way that, so that's it's a simple mode. It's a nice mode. I like it. And what's nice about it is it has a single byte per pixel. And so the VGA usually has like planar memory, which means that like, you know, some of the bytes for the pixel are at one address and some are at a different address and some are at a different location. And so it's kind of hard to just like write a single pixel in there. So what you need to do instead, or anyway, it's hard to write just a single pixel, but that's not the problem, or not a problem in mode 13H. You just, each byte is 1 pixel, so that makes it very easy to program. It has 256 colors, which we're not going to use that many colors tonight to make Pong, but you know, it's something to go with. And then it's kind of low resolution. That's the downside to it. It's 320 by 200, which even in the time was one of the smaller resolutions. You know, I think a lot of times when people think of VGA, they think of 640 by 480, but only with 16 colors in there. And so this is a trade-off between how many colors we want and all that. So anyway, that's what I'm going to do 13H. So the way, like I said, so we're going to set the video mode. And so we move to the AH register 0, because we can do XOR also. That's what I'll probably do other times. But anyway, we move 0 into that, set that to 0, and then move into AL. I'll use the C style syntax for that instead. So if we run this, so it's NASM and then QEMU. Oh, right, I forgot to get rid of the infinite loop. So let's get rid of the infinite loop. Actually, we'll move it down here. Okay, let's try that instead. No, still didn't do what I expected it to do. Oh, right, because I didn't actually call the interrupt. So we do int 10. So that's, we'll call the int instruction that they do interrupt 10. Now it should hopefully do something interesting. Nope. Let me see. It is 10H. Let's try that. There we go. That's what I was expecting. So what's going on here is the screen just turned black, and that means that anyway, that means we set the video mode to a graphics mode, and since we didn't give it any instructions to draw, then that's fine. You know, nothing really showed up there, but great. So we have that. Now let's draw some pixels on the screen. So for like I said, for this, all we have to do is write to the display memory. The display memory is at this location. It's at 0x. That's A000. Yeah, I forget how many. I forget if it's extra zeros. I think it's like that. So we, even though we're in 16-bit mode, we have like 32 bits that we can address because we have a segment and then an offset from that segment. Although I don't know, the segments are weird, and especially in the older Intel architecture. So I doubt that the 8086 can actually address 4 gigs of memory. So anyway, what we do then if we want to draw a pixel is, so I'm going to move into AX 0xa000 like that. Then I'll move this into my segment selector. So basically that means I'm going to keep this like extra segment around that I can use for talking to this display memory. And then if I want to move, okay, so now with that, let's load into AX an address for our what pixel we want to use. I'm going to try and draw one right in the middle of the screen. And so I'm going to cheat and use NASM's ability to do arithmetic on constants here. So right in the middle is going to be, it's going to be row 100. And since there is 200 pixels per row, we multiply by 200. And then we add the middle, so we want the 160th pixel there. And then what I'm going to do is write a number into memory. So we'll move into ES, AX. Let's use the color 15, which I think should be white. So if I'm lucky, we'll end up with a white dot here. No, can't do that. Okay, let's move 15. Let's try that. No, that. Yeah, so this is what we're getting to. I'm not a. Let's try DI instead. That should hopefully work. There we go, that worked. So we use the DI register. And let's run it again. We sort of got there. We have a white dot on the screen. Let me make that a little bigger. So there's my one white dot. So that's cool. We wanted a white dot, but still not. It's not in the center, which is a little bit weird. So let's see. That's 100. Oh. Yeah. It's we multiply by the width, not.
Yeah, there we go. Multiply by the width of each row, how many rows we went down, and then we do the offset like that. So let me try that out and see what happens. Great. Let's make that a little bit bigger. Um, we have a white dot in the middle of the screen, so that's cool. And sorry, I needed some more water. I don't usually like just talk and talk and talk like this, so this is kind of a fun thing about live streaming. Um, but yeah, okay, cool. So we let's draw a pixel, and cool. So why don't we try and draw a box around? So if we're gonna make Pong, we want to have a box around the yeah. So we want to have a box, and then we'll draw the paddles and the ball bouncing around and stuff in there. So let's start by just drawing a box. Um, so the first thing we want to do is I'm just going to draw the we're going to use the whole screen. We won't have any room for scores or stuff like that, but you know we can change that in the future if we need to. Um, so first we're going to say we want to use we're just going to draw 320 pixels just straight across. So the easiest way to do this is we can move into the CX register, number 320. And then we can move to DI. We're going to start that up at 0. I should probably use XOR here again because that's, I think, a shorter instruction, but whatever. And then, let's see, move, I think it's AL 15. And then we're going to do rep STOSB, not repo, rep. So what's going on here is Intel, again, because this is kind of from, so when people talk about like the difference between like a RISC or CISC instruction set, so that's reduced instruction set complexity or something like that, and complex instruction set, probably the C is for computing because you wouldn't have complex in there twice. But so an Intel architecture is really more on like the CISC side of things. And basically what that means is the instructions can do a lot more. They're very powerful instructions, whereas like on a RISC machine, the instructions do basically like arithmetic or loading things from memory, or like each instruction does exactly one thing. Instructions on the Intel architecture can really be kind of very powerful. And so one of them that they have are these, they're called string instructions, and basically they're little instructions that have a loop built into it. And so the way these work is you load the CX register with your count. So C is for count. You have DI, which is your destination in this register, and then you have the thing you want to load, which is in AL. And then you have this rep prefix, which basically says write the byte in AL to the location that it's ES:DI, and then increment DI, and then decrement CX and do that until CX gets down to 0. So it's basically a for loop. And so it'd be sort of like in C it would be like for, I equals, or let's call it, we'll use the register. So like CX equals 320, CX not equal to 0, CX minus minus, um, and then we'd say like uh, um, like that. So that is sort of roughly in sort of one line. That's probably even less readable to write it in one line of C like that, but this is kind of what we're doing here. Um, so let's assemble this and then run it, and if we're lucky, we'll get a horizontal white line across the top. Um, I can't really tell because it kind of blends in with my screen, but let's oh yeah, there we go. So we've got a white line. Cool. Um, Now we're gonna do the same thing but do the bottom. And so we like I said, it's the exact same thing. Uh, so we move in the CX 320. We move into, well, I'm going to do the AL first, the 15, or set that to be 15. And then for DI, this is choosing our starting point for where we want to start drawing the line. And so for this one, we want to do it on row not 200 because everything's it's zero base, so it's 0, 1, 2, 3 up to 199. So we'll do 199 times 320 pixels per row, and then we do rep to OSB. So let's see what that. Whoops. We're sort of like getting there. We ended up with one dot down at the bottom. What did let's see. Set this dx to that. Oh, I did repo, not rep. You would think that NASM would complain about that, but maybe repo means something else. Let's try that. There we go. So now we've got our white line on the top. We've got our white line on the bottom. So we're like halfway to a Pong grid. And now we're going to do the horizontal lines. So let's see. Let me add some more comments here. Then we're going to draw the bottom line. And then we're going to draw the sides. I'm going to do something here that is kind of cheating, and it's probably terrible from an instruction or like from a programming speed capability or whatever, but it saves us a couple of instructions. So in theory, it makes the code smaller. Anyway, I'm gonna do it because it's fun. So what I'm gonna do is you don't have to write to memory 1 byte at a time. We're in 16-bit mode, and so we can actually use 16-bit memory operations. So 16 bits is 2 bytes, and since every pixel on the screen is 1 byte, we can actually write 2 consecutive bytes at a time. Okay. And the cool thing is it like wraps around. So if you go off the right side of the screen, it comes back around to the left side of the screen. And so what I'm going to do is basically write 2 bytes onto the rightmost column of the screen. And what that'll actually do is draw me a vertical line on the left and the right at the same time. Okay. I don't personally so I'm not like a expert assembly programmer, so I don't personally know how to if you can do this reps to OSB thing with a different stride for it. So not instead of counting by 1, you could count by like 320. So instead I'm going to do a for loop basically. So what we're going to do is we're going to start by moving into DI the offset for our first line. And so like I said, we don't want we want to basically do one pixel from the left. So that'll be pixel 319. And then I'm going to use the CX register again because that's a good counting register. We want to draw 200. Basically the columns are going to be 200 long, so I'm going to move into CX 200. And then I'm going to have let's say loop. I should probably call this something a little bit better than loop, but this will work well for now. So we're going to move into ESDI AL. Oh, you know what? We already wrote into AL up there, so we don't need to do it twice here. So let's delete that one also. Okay, so we're moving into ESDI, the AL byte. And then we want to add to DI. So we're going to count by 320 each time. So we go one row at a time. And then we want to subtract from CX 1. And then what we want to say is, hey, if we're not to 0 yet, we want to go back up to the top. So for Intel syntax, that's J, and then there's a bunch of condition codes. So I use J and Z, which means jump if not 0. And we go back to loop like that. And so this is just a very simple loop that hopefully we'll draw 2 vertical lines on the side of the screen. So let's watch and see what we end up with there. We're sort of there. Interesting. So I don't know if you can, how well that shows up for you guys. Yeah, that's kind of weird. That's not what I expected.
So we've got one horizontal row there. We got a horizontal row on the side. We got one over there and then one over there. I know what we did wrong. We were only using byte-wise things. We want to move AX. The other thing we need to do then is we want to actually write two different pixels. So we're going to move into AX 0x 0f 0f. So that's 1 byte of 15 and then another byte of 15 is what that says. So let's try that. There we go. That is a nice white square. This will be a great grid for Pong. You know, I think it looks pretty good. Cool. So now, what should we do next? Why don't we do? I guess one obvious thing is to draw the paddles, but I think that's a little bit less interesting. Why don't we try doing the ball instead? Okay. Let's see. So this, I'm going to rename this to main loop, and the reason for that is because it's sort of the main game loop. Whoops. Somehow main game loop turned into main goop in my head. So that, like, I don't know, it'd be fun. So from now on, basically, all of our code is going to fit inside of this loop. And then, let's see. We also need to do. We're going to want some variables now. So let's use. Let's have ball x, and that's going to be. We need. Let's do 2 bytes because 320 is more than 256, which is the most we can fit into 1 byte. So we use DW for that. And let's start the ball out at 160, and then we're gonna have ball y, and that's gonna be at we could do a byte for the ball, but I'm gonna use a word also just to kind of keep my types the same. I think that should be fine. So we'll have each of those. We're basically just sticking data, like intermixing data with our code like this. And so we're gonna have to use some care to make sure we don't have any, we don't try and execute the code or the data. I mean, you can, it'll run, it'll probably crash the processor though, because I don't think this is gonna be a legal instruction. Actually, we can find out if we disassemble it. Oh yeah, sorry, it's because I have all 512 bytes in there, it feels the need to do all of them, but like, yeah, let's see. Yeah, we can see our code. Yeah, so this is actually, I think, what the what is that actually? I don't know. I think that's our data there. So it is actually a valid instruction. So who knows what'll happen if we run that? Probably security vulnerabilities, because that's how you get a lot of security vulnerabilities, is you execute something you didn't mean to execute. Cool. So for this, we're gonna draw the ball to start with in our loop. So basically all we do is we want to move into AX. We want to load from memory. So if I remember right, in NASM or in assembly language in general for Intel, you use these brackets to load from memory. If not, it'll probably complain to us. So we're going to use our ball X, and then we're going to, multiply AX. Sorry, we use IML. I always forget about that. IX by 320 to, no, sorry. Let's load the Y coordinate first, and then we multiply that by 320 to turn that into like an offset into the array. And then we want to add to AX the ball X coordinate. Okay. This is where that CISC versus RISC thing comes up again, because here we're doing something like we're adding and loading from memory at the same time, and that's, on RISC, that's not what you would do. You would load and then add. So anyway, that's actually, to be honest, I'm not sure it'll work, but it looks like it did. Great. So and now we want to draw the actual pixel there. So let's move. We move into ES
Oh yeah, we need this to be into in DI, so let's move AX into DI. I don't know, could have done this some other way, but whatever. And then we're gonna move into our ES DI 15 like that. I'm hard coding it there, and hopefully it'll work this time. Maybe if I do move B, that'll. Let's try that. No, because move B is not an instruction or whatever. Does that do it? Yeah, there we go. We said that. So there's some ambiguity there about do we want to move 1 byte 15 or do we want to move that as how many do we want in there? So tell it it's a byte, and now let's run it. If we're lucky, we'll get a white dot in the middle of the screen again, which we did. So that's cool. We're on our way now to doing this, to getting this to work. The next thing we want to do is what do we want to do? We also, so now we need the ball needs to move, right? It's Pong, it's dong 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 dong. So we need to do that part of it. So let's also down here take let's have a little more. So let's do ball. I'll call it DX for the speed, basically. So it's a byte. We'll say it starts going 1, and ball dy is also going to be 1. I'm just using bytes here because it's only ever going to be 1 or -1. And anyway, yeah. So let's say so we're going to update the ball position. And so yeah, I guess I already clobbered that register, so I'm going to reload it from memory. That's a little bit less than ideal, but if we have time, we can redo this. Anyway, so let's move. Let's load into AX again. Ball X, and then we will add. What are we gonna do? Let's see. And let's move into. We have BX also. That's a good register. Let's move ball DX. And now we're going to add. Actually, you know what we can do? Let's do it like this. So let's move, or let's clear out BX. So we XOR it with itself to set it to 0. We're going to move into BL ball DX. You know what? I'm gonna stop trying to say bytes because we're like nowhere close to running out of bytes. So let's make these words instead. So there we can get rid of the XOR. And now we can just say add into ball X. Oh yeah, BX. That's what we do. Okay. And then we're gonna do the same thing now for Y. So we move into BX. Oh yeah, that needs to be like that. Ball DX or DY, sorry. And then we add into ball Y BX. Okay. So if we run this, it will probably crash. Is what's going to happen because I didn't put any bounds on it. But let's run it and see. I'm actually surprised it didn't crash any sooner or like kind of immediately. Let's run that again so we can see it in slow motion, or maybe not slow motion, but slower motion. So we ended up with a diagonal line. The ball's moving, and then it's just kind of going all over the screen. So that's cool. It's moving, but we've got to get a little more control of it. So there were a couple of problems we saw there. One is it completely ignores any boundaries, and then 2, the ball doesn't actually get erased, so it just keeps going longer and longer.
It's more like a snake or like a trail that goes on there. Um, so what we're gonna do instead is say, let's see, how do we want to do this? Um, okay, let's make it bounce first. And so what I'm gonna do is basically by testing the color of what's there already. We could hard code like the bounds and do bounds checking and all of that, but I think I'm just gonna like cheat and say let's read the color of the pixel that was there first, and then check on that to see did it hit anything. Okay. So the first thing we'll do, I don't think we're using CX here yet, so let's move into CX ESDI. Sorry, let's do CL. Just load that 1 byte, and then okay. So the first thing we're gonna do is let's see. The question is, which way do we bounce? Do we want to bounce left or right or both? Yeah, this is going to be a little tricky, I think. We'll try it out though and see what we can do. No, okay, I'm not going to do this. Looking at memory instead. I think instead what I'm going to do is just like we said, looking at the like hard or like the bounds that we have. So first we're gonna so let's say check bounds. And so we're gonna check first against either like the horizontal walls. So let's say let's see. I think we can compare straight from memory, but I'm not sure. We'll try it out and see. So we're gonna compare ball Y with 0. And then let's see. So if it is equal, we'll do some stuff down here. So we'll do J and E to skip. This let's say like I don't know. I'm just gonna use like really bad labels and call it A. So if it's not equal, we're gonna get an A. If it is equal, then what we do is we're gonna flip the sign of our direction for Y. I was thinking of doing this with X, so let's switch to X. So I think we can multiply straight into memory. If not, Nasm will complain. And let's do -1 as a byte. I think that works. Let me see if Nasm. Nope. So what are? Oh yeah. Forgot we need our sizes. Oh yeah, it doesn't like this. Let's see. Let's move into AX -1 then. No, that doesn't work either. Okay. Let me check my let's see, x86 assembly reference. There's one that I like. Let's see if we can find that one. Oh yeah, this. What do you know? It came up first. Let's get a little bigger. IML. Okay. That's probably smart. Multiply is an expensive instruction, but it looks like you can't actually do you can't actually, it looks like, do a read from memory and write to memory with a multiply at the same time. So, so what we have to do instead is we have to, let's see. There we go, we'll do that. So we'll load our dx out of memory. And then we will, we compare with 0. Actually, let's do this. Whatever, we'll do it up there. It doesn't really matter that much. Then we can multiply our ax by -1. And then we write it back into memory. Like that. Okay. Cool. So we compare if the x position is 0, that means we're in the first column. That means we want to balance, we want to reverse our x direction. So then if we're gonna do basically the same thing now, except, and I'm just gonna be bad and duplicate code. But this time we're gonna compare it against 319, so the last column. And we can do the same thing. There's probably a way to shorten this code, but I'm gonna not worry about that for now. Okay, cool. So now we can at least get our x and y bouncing. Now we need to do the same thing for y, and I'm gonna cheat again basically, and okay. So now we're gonna do the let me add some more comments. So let's see, check x bounds, and then we have yeah, down here is going to be where we check y bounds, and we change all of our x's to y's, not all of them because we can't rename the registers, and then so we need to change our labels also. So this is going to be C and then D. And then D there. And then we need, we're going to compare against 199 and 0 for Y. And we want to skip all of the sections that we don't need to worry about. So here, this is the case where we've hit the left wall, and if that's the case, we can't also hit the right wall. So we'll go ahead and skip the test for the right wall. So we'll jump to B. You know what? Let me those are good names here. So we're gonna say like left wall, and then the dot A is gonna turn into right wall. Okay. And then oh wait, yeah, it can't we don't want to jump to the right wall there. Oh yeah, we want to jump to we'll call it top. And this is going to be top then here. Okay. And then this is bottom. Where do we go here? We don't want to go back up there. Oh yeah, we want to go to done. We'll just call this done. That works. Okay, and then the same thing before. If we hit the top wall, we don't want to run anything, so we want to jump to done, like that. All right. So I don't think we're going to see anything super interesting here still yet, but whoops, main loop.b, where is, oh yeah, that's line 56. Where do we want to go here? Oh yeah, we want to jump to top. Cool. So let's run it and see what it does. Hey. Interesting. It looks like it doesn't. It can't actually bump into every single part of the screen, but we've got it doing this diagonal view on it, which is good. That's what we wanted to see. So very cool. All right. So let's try the other problem, which is that we need to erase the old position for the ball. Um, I think, hmm. So the easiest way to do this is just down here at the end, after right before we update the ball position, we can erase the ball. I think this is going to make it flicker, but it's probably about the best we can do. So let's erase the ball. We do that just by drawing the ball, except instead we actually no wait, we haven't changed DI this whole way. So we basically just want to write let's see, move into ES DI 0 to turn it black. Okay. I think we're going to end up erasing the walls very slowly while we do this, but let's try it out and see. Oops, operation. Oh yeah. We want to do a bite. There we go. Yeah. Okay. So that's going really fast. We don't actually ever see the ball, so we're going to add a loop to slow it down. Um, and if we wanted to be like fancy, what we would do is like set a timer and sleep and like actually go to sleep for a while and wait for the timer to wake us up. But that's more time than I really want to worry about. So instead, I'm going to do a busy loop basically. So here, let's move into our CX or register CX, I guess, not RCX. That's a 64-bit register. I'm going to set it to like the highest value I can have in there. And then we're gonna sub CX1 and then J and Z. So jump if not 0 back to we're gonna call this delay loop like that. I doubt this is going to be like 65,000 is not real long on like a modern CPU. So I doubt this is going to be enough to slow it down, but let's try it out. And now we're sort of getting there. We see every now and then. So let's make this go a little bit longer. What we're gonna do now is do move into DX. Let's try like that. We're gonna so now we're basically just gonna do a double for loop inner. So we'll have a outer delay loop and then an inner delay loop, and it's just gonna be the same thing. And then J and jump not 0 to delay loop inner. Okay. And we'll probably just iterate on this until we get to a speed that we're kind of happy with and see how we do. There we go. That's looking a little bit better. I think that should still be a little bit slower. So let's try changing that to 2. Oh, I didn't actually compile it. It's looking a little bit better, I think. Yeah, we'll try maybe just a little bit slower. I think it's still about half the speed again, I guess. We don't want this to be necessarily a super hard version of Pong. There we go. Here, I'll make this bigger too. Cool. Yeah, we've got a little dot moving around, so that's looking good. And let's keep going then. Um, so the other problem we saw is that it's erasing the ball or the edges of the thing. And I think that the problem is we want to move the bounds in a little bit closer. Um, so let's see. Oh yeah, so instead of comparing a 0 and 319, we're going to do 1 and 318. And then instead of comparing the top and bottom against those, we're going to do 1 and 198 instead. And I think this should work. Yeah, there we go. Cool. Yeah, I think this is looking good. All right. The next thing we want to do is some paddles. So I'm going to add a couple more variables here. So let's do we'll have two paddles. We'll have P1 pause or position. We'll just have this be another D word. It doesn't really need to be a D word, but you know, again, it just kind of makes everything easier to keep the sizes all the same. And let's start off at like, I don't know, we'll start at 25. So what I'm going to do is I'm going to use this as the position for the top of the paddle, and then we're just going to have a fixed size and move them up and down like that. So we only have to keep track of one variable, basically. We're not going to worry about having the paddle change size. So we'll start the player 2 also at, let's start them at like 75. And the reason is just that way we can tell the two players apart a little bit easier. And so with those, we want to draw the paddles. So let's do that maybe right up here after we draw the ball. And let's see, what we're going to do is... Actually, let's draw the paddles first. So we're going to move into DI, or sorry, let's move in AX. We're going to load P1 pause. We're going to, let's see, multiply that by 320. So we do imul AX 320. And then we're going to add to it an offset. So add the horizontal position of the paddle. Okay. I'm gonna set it at like 20. We can tweak this if we want to. So we're gonna add to AX 20, and that gives us the horizontal position. And then we're gonna make a loop here. So let's move AX into DI because I like DI. I don't know. And then we're gonna move into CX, the size of the paddle. So we're gonna move into CX, the size of the paddle. Let's make it 50. We don't want to make it too easy or too hard, so we'll try that. That's you know, basically 1/4 of the screen. So we'll try that, and now we're gonna do a loop. So we'll call it P1 loop. And so what we do is we move into ES DI 15 because we just like everything being white here, I guess. I don't know. And then we want to add to DI 320, and then we're gonna decrement our CX. So subtract CX or from CX1,
and then jump not 0 to P1 loop. Okay. And so let's, again, because I like running everything like over and over and over again. Oh no, instruction inspected or expected. Where? Oh, right. DW, not DX. Okay. Instruction size not specified. Oh, yeah. This is kind of cool. I never, this is a dumb thing, but I never really knew why you had the right byte sometimes in your assembly instructions, but like that's why it's because otherwise it doesn't know which opcode to use. That, man, that's interesting. I wonder what happened there. That's really bizarre. What is going on? Okay, let's go figure this out. Whoa. Yeah, what? Okay. Um, that is so weird. Um, I bet I overwrote a register that I down here assumed had not been overwritten yet. Which one was it, I wonder? No, okay, so I draw the ball later. Um, Clear my terminal there. Okay, then I erase the ball, update the ball position. That is wild. Did I call that the wrong thing? Like, sorry, I'm not talking a lot right now. I'm just like, what's going on? Um, oh man, what's going on here? Let's see. Um, do. Okay. Um, yeah, we add the horizontal position of the pedal. We multiply by 220. We load the position. Um, AX, DIAX. Okay. Let me run this again and see what's going on. So it looks like it started off trying to draw the paddle over there. Let me change that to 10 because if that's really what 20 looks like, that's further away off or further from the side than I wanted it to be. So let's try 10 down here. No, that is bizarre. What's um P1 pause is 25. Yep. Oh, you know what it could be? What am I using DX for? The DX register, that is. Um, no, that shouldn't matter because I clobber it there and then subtract it.
So what I was wondering is the multiply instruction, because when you multiply two 16-bit numbers together, you can get a 32-bit number back. And so it's got to put the top half of the number somewhere, and so Intel puts that in the DX register. So that's what I was wondering with that, but that's not it either. Man, this is let's see. Okay, so we load the position, multiply by 320, add the horizontal position, and then oh, there's our problem. This is backwards. So we move into DX from AX. Let's try that. There we go. So with that done, I think I actually like 20 better for the paddle position. So let's try that. Yeah, so I had the direction on my moving wrong, and so that was really weird behavior that it came up with. It's not what I would have expected it to do, but anyway, yeah, that looks good like that. Cool. So we have one paddle now, and then we're gonna do basically the same thing, but draw the other one. And so I'm just there's probably like really bad coding quality, but I'm just gonna copy it instead and do it that way. So this is gonna be P2 loop now. So here we load our P2 pause instead. And then the horizontal position. So instead of being 20 from the left, we want to be 20 from the right. It's 320 wide. So we'll just call this 300. We might be off by a pixel or so, but it doesn't really matter. We just pick something that looks nice. And there we go. Now we have two paddles. Looks pretty good, I think. And the ball goes through the paddles, but I'm not going to worry about that because that's easy enough to fix later. But why don't we work on trying to move the paddles instead? Okay. So for this, we're going to need the keyboard, and we're going to want to use the rough bounds interrupt list again. So there's a bunch of keyboard. Forget the name of the keyboard. Does this it here? No, that's not it. Oh, I have some. Oh, excuse me. Okay. Here we go. Now we have the keyboard. We want to check for a keystroke, and then if there is a keystroke, then we'll actually read the keystroke. So let's see. So we're using interrupt 16. It says to check for a keystroke, you set AH to 1, and then it returns to say if there's a keystroke available, and scan code and ASCII character and all that stuff. Cool. So what we will do is basically say, let's do it. So after we draw everything, we check our bounds, and then we also want to check our keystrokes. So let's do it and be here before the delay loop. Let's see. Slow things. Okay. So to check for a keystroke, like I said, it was we have our AH. So we move into AH 1. 01H is the same as just 1, so we're just going to do 1. And then we let's see, what do I want to do after that? Oh yeah, we do the interrupt, which I think was 16, right? Yeah, so do 16. And now we want to see how to tell what's the result. So this says it sets the 0 flag if no keystroke is available, or it's clear if a keystroke is available. So basically, we can check and see whether like 0 just came back. Is like we can jump on 0 to decide whether there's a key or not. So let's say down here is going to be no key.
So we'll say, was it, sorry, the Z flag, zero flag is clear if keystroke's available, so it's set if not. So we're gonna say JZ, so jump is 0 to no key. Otherwise, what we're gonna do is uh, actually read the key. So we do this in 2 steps. We first check if there's a key in there, and then if there is, then we then we read it, and otherwise like we skip it. Okay. But to read it, we have to make another BIOS interrupt call. So we use the get keystroke function here, and this works actually basically the same. It just doesn't set the flags for us because I think it actually blocks until there's a keystroke. So it returns the scan code and then the ASCII character in AL. So that's what we're going to use is the ASCII character. So we want to move into AH0 because that's what we use there. And then we want to do interrupt 16 again. And then now AL has ASCII code for keystroke. And now what we're going to do is basically keep checking that whatever. We're going to check it against a couple of keys that we care about. So I'm going to use W and S for up and down for player 1. And then I'll use I and K for player 2. So what we do is we want to say compare AL against W. And we can use jump if, let's see, JNE to, let's see, test S is what I'm going to call that. So JNE to dot test S. If it was W, that means go up. So we're going to add, or sorry, up is actually lower numbered rows. So we're going to subtract from P1 position 1. Okay. Cool. So for S, we do the same thing. But this time we test against S. If it's not going to be us, we're going to test against I. And then in this case, we want to add 1 to the player 1 position. There we go. And then we have dot test I comes after that. And we do like the same thing again. Except we test against I and then K. And then we're changing our P2 pause here instead. But why is that? Oh yeah. We'll just jump down to no key because we're at the end of this thing. Okay. So we should be able to move our paddle now. Whoops, forgot a bunch of stuff. Oh yeah, these all have to be words. There we go. Oh yeah, I forgot the colon also. There we go. Cool. Let's run it. That's not good. Wonder. Okay. There's a couple of things we're gonna want to do right now. This is only reading 1 keystroke per frame, which means that like only 1 paddle is gonna get to move each time, which could be a problem. So we may want to do this in a loop, but that's not actually the problem that I'm running into right now. I don't think. is going on? That's a little bit weird. Let me run again and see. Yeah. I bet I did something like got the directions wrong again. Oh, I had to do int 10h there, so maybe maybe I need to do int 16h again down here. That if I called the wrong bias interrupt, that could be the problem. Oh wait, I forgot to actually like compile it. Yeah, because what's probably happening if I'm doing 16 decimal, that's the same as 10h, and so I'm probably just setting the video mode over and over and over again. This looks better, and now, okay, cool. Oh no. Yeah, okay, cool. So that's sort of working. But we were not erasing the paddle again, so that's kind of a problem. I think what I'm going to do here is just kind of cheat, and when I go and draw the paddle, I'm just going to start by, oops. I'm just going to draw a black spot on either side of the paddle, and that'll basically have, since we can only move one position per frame, that'll just have the same effect as erasing the paddle. So it's kind of hacky there, but whatever. Let me see. So basically at the end of the loop here, to erase the bottom, since we've incremented di from the last time, we can move into es di byte 0, and then do the same thing down here. Byte 0, like that. Okay, and now we need to erase the top also. And so I think we can. Okay, I'm gonna see if we can just do it with an offset. So let's do move es di minus 320 byte 0. Let me see if Nasm likes that. Hey, it does. Great. So we're gonna do the same thing then before. Okay, so what this is doing is it's saying we want to move into the memory address relative to segment ES. If it's like DI, so our data index register or destination index. But we can have a small fixed offset to it. So we want to offset by 320 bytes. So I think this should work then. So let's see, if I push W, the paddle moves up. Push S, the paddle goes down. That's weird that if you hold it down, it keeps going. Yeah. Oh, weird. Oh, and K doesn't work. Oh, so you know what? I bet I know what happened. I bet my copy and pasting, I got something wrong. Oh, yeah. Here we go. I'm comparing against S. So we want to compare against K. Let's try this again. Cool. Yep, down. Okay, S only moves one. K moves that one down. And cool. Great. So now we have two paddles. We can control them with our keystrokes. It looks like they do eventually move. So hey, what do you know? Cool. So now I think the next step is to we have to do bounce checking against the paddles also. So okay. One thing I'm gonna do is I haven't committed this code like in a while. So I'm gonna add my boot.asm file and then do commit, let's see, Pong board with movable paddles.
Okay, the other thing I didn't add is bounce checking on moving the paddles. I think I'm not going to worry about that and just say, hey, if you're playing, be careful, don't move off. If you do move off, you probably get to write in all kinds of interesting memory, and maybe there's fun things you can do with that too. But yeah, so what we want to do is in our so we want to bounce check against the paddles too, and uh, basically we just need to do this in the X bounds. Okay, so we're gonna reuse a lot of our code here, and to add another label here, and let's call this flip X. So what we're gonna do, so we do a comparison here, and we're gonna say J E. So if it's equal, we're gonna go to flip X. Otherwise, we fall through. And then here we're gonna compare it with, we're gonna compare ball X against word. I should really be using constants for this, like if I was being a good programmer, but I'm not going to. So let's do we'll just hard code 20 in there. So 20 is the location of the ball or the left paddle. Actually, wait, we want to do 21. And if because we want to check on either side of the paddle because we can hit it from either side. Man, I should figure out a better way to do ors than just a bunch of control flow, but I'm just going to do it with a bunch of control flow because that's the tool I have right now. Okay, so if it's equal to 21, so what we need to do is we need to say if ball X equals 21 or ball X equals 19. And oh man, we have to compare against ball Y too. So we also need to check the vertical position and make sure it's not equal to the ball position or the paddle too. So yeah, so ball Y yeah, so we want and ball Y greater than or equal to P1 pause and is less than P1 pause plus I made them 50 long, I think. So there we go. So this is the condition that we need to encode now. So here's our if it's equal to 21 and so let's have a check vertical bounds. Okay, so if they're equal, we go to check vertical bounds. Otherwise, we want to compare against 19. And if they're equal, we go to check vertical bounds. Otherwise, down here, we want to skip all of this and go to the right wall check. So let's jump to right wall. Okay. Let's call this jump vertical or check vertical bounds P1 because I'm just going to be terrible and like duplicate this again later. Okay. Okay, so what we're going to do now is we're going to load, what's a register we can, ball dx. So we don't want to use the AX because we're using that. I think we can use BX. So let's move into BX. Let's see, ball Y. And now we can subtract from BX P1 pause. Okay. And now we want okay, so subtract I think also sets the condition flag, so we can kind of use that as a comparison. So if it's let's see, JL, so if we're less than 0, we want to go to the right wall check again. Otherwise, this means we're greater. So if we're in this place, it means that we're greater than P1 pause. And then we want to check and see if we're less than 50. So let's compare BX with 50, and then and we want to, if it's greater than or equal to, so JGE, we go to a right wall, and otherwise we fall through here to flip X. Okay. I think that does it. Okay, cool. Let's try it out, and if this is working right, we should have the ball bouncing off of the right paddle, or the left paddle, I mean. So let's see if I can make that bigger. And oh, it looks like I can actually speed things up too. I've made this much slower. Let me speed it up. Yeah, I'll go back down to 10 and make it like 4 times as fast. Uh-oh. Okay, here we go. Man, this is getting super choppy. All right, cool. It bounced off I don't know if anyone saw that, but it bounced off the right side of the left pedal. And now I want to see if I can get it to bounce off the other side of the... Whoa. Oh, missed my chance. Oh, that's funny. Look, if I go off the top, then my paddle comes to the other side. So let me, there we go. Let's get out of the way. Okay, I think I can get down here in time now. Nope. Oh, too slow. I'm too good at Pong. Here we go. Whoa, whoa, whoa. Let's get up there. Let's get up there in time. This game is so slow now. There we go. All right. Cool. So bouncing is working on the left pedal, and we're just gonna do a bunch of copy and paste now to do the other side. Man, I've made this like super slow, but whatever. I'm not trying to make this good, just work, you know. Cool. So now we're gonna check against the right paddle, and this is gonna fit into the same spot. So let's do JL. Okay, so we flipped the switch, we flipped the sense of that last jump, because before we would fall through into the flip X case, but we're gonna add some more code to check against the other paddle. So let's copy and paste my code again. At some point, I bet Nazm's gonna complain that I've run out of room in this segment. So that's okay. So in this case, but if it does, that's that. So I put the other, let me scroll up just to make sure, but I put paddle 2 at position 300. So we're going to check against 301 and 299. So 299 and 301. And then we're going to have to compare against P2 pause instead of P1 pause. Okay. So we basically just like copy a bunch or change the numbers again. So we have 299, we have 301, and P2 pause then here. And so yeah, in this case we go back to JGE. And I think that should just work. It should be enough. Oh, right. It's check vertical bounds P2 now. There we go. Oops, did not work. Not at all. Not in the slightest. Okay, so it doesn't work if we're coming at it from the right side, but let's see. Maybe I can get it to work from the other side. Nope, didn't work there either. Let's see. So we, oh, right, because I went back to P1 instead of the P2. There we go. You know, if I were doing this, I don't know, for real, I would probably use a like a function there to abstract this a little bit better, but you know, oops, I think I just missed there. Oh, still didn't work. Okay. Oh, right. We need to jump to right wall, not to. No. Okay. So we jump to right wall, and maybe this will make it work. There's a reason why people quit programming with go-tos, because it's sort of hard to keep all your labels straight. Nope, still went through on that side. I'll try the other side. Nope, still not working. You know, I may not even be running this at all. So okay, so there's less than, we go to 50. Then we get in here. Okay, so we compare ball X against 299 and then 301. Vertical bounds P2. And otherwise we go to right wall. Oh, right. Down here we don't want to go to the right wall. We want to go to so we want to check paddle 2. So instead of going to the right wall here, we want to go to check paddle 2. That's probably it. And we need a colon. Okay. Was it like third time's a charm, fifth time, sixth time, whatever we're on? Ah, still didn't work. Nope. Hmm. Here we go. Yeah, we don't want to go to right wall there too. We also want to go to check paddle too. Okay, so we're run again, and whatever time we're on, this one's a charm. There we go. Okay. And I'm gonna check the other side too. Oops. Might as well play both players if I'm gonna have to wait for the ball to go around. Here we go. Oh, 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 get up there, get up there. Oh, too slow. I think there's like basically no way for me because I made the paddles and the ball be the same speed. I think there's actually like no way to catch them, uh, unless you just follow it carefully. But whatever. Oh no, no, no. Get there. Okay, good. Good, it worked. Cool. I was able to test it out. Yeah, so we've got basically a functioning game of Pong. I don't know. Maybe let's kind of just to finish it up, like, there should be some way for you to lose the game, I think. So why don't we make that happen? So, let's I'm gonna add a label here for like begin game. Um, so what we're gonna do is we're gonna make it so that whenever the ball gets to either the left side or the right side, we're gonna jump down to a new portion of the program that will print out a string that says player whatever wins, congratulations. And but to do that, since I don't want to bother with trying to go find the fonts and render the font myself, we're gonna do instead switch to text mode and draw some text that way instead. Okay, so let's see. Let's make two labels way down at the end of all of this. I mean, the labels can go anywhere, but we might as well put them down at the end. Let's do player 1 point and then player 2 point. Both of these go back into the begin game at the end. Again, there's going to be a bunch of copy and paste because I'm kind of lazy, but whatever. And then let's add some extra. Let's see, player 1 message, and let's see. This is going to be. I think we can do this as a bunch of bytes. So we can say. Okay, so player 1 scores, and then we're gonna null terminate it because that's what I like, or it's I think a little bit easier to do it that way than keeping track of the length. Will be again bytes. This is gonna be player. And we null terminate it again. Oh, you know what we can do? Oh, I'm actually gonna do some code reuse for like the first time tonight. Okay. Um, so down here we're gonna have a thing, a method. Okay, let me rearrange all my labels and stuff. Um, so we're gonna have a label down here called drawString. And what we do is here we're gonna move into si player one message, and then we jump to drawString, and then here we move into si player two message. So SI is it's a register called the source index is kind of what it stands for. That's the mnemonic for it. And so we're going to basically copy a string out of this message up here. If I wanted to try and save every single byte, I would do something like do player and scores and just do the different number, but like whatever. Let's see. So the first thing we want to do is we need to go into text mode. So I think we want to use mode 3 for that. I think that's the text mode we usually use. So we're gonna, let's see, XOR 0 out AX, move into AL 3. That's the mode we want. And then we're gonna do int and H. So this switches us into text mode. Then what we want to do is, I was scrolling back up to the top to make sure. Yeah, that's cool. Then what we want to do is go up to, oh yeah, so we're in text mode. In text mode, let's use AX first. In text mode, the text memory is in a different location in there. So let's go back into our, oops. There we go, interrupt 10. Set video mode. So we're going to be in mode 3, which is our 80 by 25 text. It's kind of the standard text thing. And this says that this is in B800. Okay, so we want to use B800, move AX into the extra segment register. And then, let's see. So then what we want to do is we want to pick somewhere to put the text. Let's just stick it in like the center. So it's 80 columns by 25. Let's put it in row 12 or so. So we want to move into the destination index. That's going to be row 12 times 80 because we have 80 columns. And then we're going to move into SI. That's going to be, oh, wait, we already have SI because we did that up there already. So now what we want to do is we're going to go byte by byte and right into the memory. So we have a string loop is what I'm going to call this. Let's do a dot for that. So we're gonna start by so we could normally use like until the CPU's got the string copy or like string, basically like mem-move is a built-in single instruction in the x86 processor. We're not going to use it because in text mode it's actually 2 bytes per character instead of 1 byte per character, because it's 1 byte to tell you what character is there, and then it's another byte to tell you stuff like what color it is and all that stuff. So because we got to count by 2 and we have to count by 1 in one string and 2 in the destination, and it's easier just to write our own loop. So for this, let's see, let's have exit loop. So we'll have another label there because we're gonna add a little bit of code here too. So what we do is we move into AL DI, or sorry, SI. And that should be relative to the right data segment. If not, we're going to get weird behavior. If it's 0, so if it's the null terminator, we want to exit the loop. Okay. Otherwise, what we do is we move into ESDI AL. So we take that character and we write it into memory. And then we want to advance the cursor or the text position by 2, and advance our string position
by 1. And then we go back up to the string loop. Okay. Cool. So that should write us the right string. Now we just need to go down here or go back up to where we were doing our comparisons and change where they go to. Let's see. So if we hit the left wall, instead of going to flip X, we don't just bounce off the left wall. We want to go to, so this would be player 2 point. So this is if the player 2 scores a point. And then the same way when we check against the rightmost edge, so we check against, down against right wall. That's 318. Instead of going to top, we go to player 1 point. Okay. So that should be good. The other thing we want is we probably want to do press any key to continue. So I'm going to copy this loop again because that's just kind of the easiest way to do it. Let's see. Yeah, that's where they exit the loop. We want to print press any key to continue. So let's do, we'll put it down here at the end here. Let's see. This is going to be some more bytes. Press any key to continue. And we null terminate it. So here we move into SI, press any key. And we move into DI. Let's go to row 14 times 80 again because we're at 25. And then we're just going to copy this and rename our loops because, again, I could make this a proper function call, but I just don't really want to. That's what I mean, or what I mean. Okay, and now we actually want to wait for a keystroke, and so this is where, if I'm right about my bias calls from before, where I thought that the interrupt 16 waits for a keystroke if you don't check for one first, we should just be able to wait for a keystroke. So let's let me go up here and remember what that is. Here we go. Yeah, we just want to use our 16H with AH be 0 equal to 0 again. And there we go. Cool. And I bet we're going to want to clear the display again too, but I want to run it and see if this works before I... Oh no, something wrong with 234. Oh, right. You don't need a comma there. Cool. Oops. Okay, I did something wrong. I bet it's up here in my loop where I'm testing things out again. Where is that? Oh, yeah. Oh yeah, so we're drawing the petals, we draw the ball. I'm really glad that I wrote some comments because this would make no sense otherwise. So we check the left wall, compare if they're equal, we go to player 2 point. Otherwise, we check the paddle. And then where do we go to the left wall? Okay, that's where we check paddle 2. And then the right wall. It's weird that right wall is... Why did I put it there? That's a good question. Oh well, whatever. Um, okay, so right wall, we compare against 318. If it is, we go, oh, well, we want JE, not JNE. Okay, and then we just don't want to do this here at all. Okay, I'm not going to delete that, and I'll comment it out because I'm a little nervous about that. Okay, let's see if looking better. We'll let it hit the wall, and it should say nothing. That's not. Oh, the other thing we have to do is we have to reset the game. We have to at least reset the position. So, so here we go. We're gonna move into ball X. Let's reset it to 160. Move into ball Y 100, and maybe that works. Oh, that got way faster too. Okay, so we went into text mode, but I don't see anything. This is weird. Yeah, I don't know what's going on with that. But okay. So something here went wrong. Move AL SI. We add them. Yeah, that looks good. And reload. Press any key. Yeah, we have begin game up there. So we set the video mode 13, load the memory location, we draw the boxes. Yeah, this should just work. You know what, let me try a few other cases and see. Okay, so I'm gonna see what happens if the player one loses now. Maybe that. It'll probably do the same thing, but we'll see. Okay, so we switch into text mode. It is waiting, and then we push a key. As yeah, I don't know what. Yeah, so I guess you can't see me typing on the keyboard, but I'm pushing keys, and it tries to switch back into uh, video mode, but it falls apart. So that's kind of weird. Huh. Oh, let's see what's going on. Oh well. Yeah, I wonder. Okay, so there's two problems right now. One is that the game doesn't reset the way it's supposed to, but the other is that it's not drawing the string the way it's supposed to either. So I should probably break these down one at a time. So let's try to figure out why it's not drawing the string first of all. So So we load from SI. If it's 0, we exit the loop. Otherwise, we go, we advance. Like, I don't know. I've been over this. Yeah, it's B800. Is that what I typed up there? Yeah, that's B800. And so then 10H for text mode 3. Yeah, that should be working. Okay, I'm gonna play again. Just think like while I think, might as well play. Go 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 go. Okay. Here we go. Oh no, I don't think I'm gonna make it. Oh oh oh. Oh, just in time. Cool. Okay, this time I'm gonna let it hit a wall and see if I can figure out what's going on. Okay, so we go into text mode. That's good. That's what we wanted. Oh no, didn't mean to grab my mouse. There we go. So push a key. It tries to draw the screen and then it like goes back. So there's something about when we get to that first test where it fails again. We load ball dx right, or sorry, we load ball x right out of memory, so that should be fine. And we do we write to? Yeah, okay, let me find where we go to begin game just to make sure. That should be the only place. Yeah, so we said begin game and that. Okay. I'm gonna comment out some code and see if that helps us any. So let's get rid of these two loops. They're I feel like most likely to be problematic. Let's try that. Well, that's interesting. I think I just forgot to build this the last time. Man, I just wasted like 10 minutes because I didn't actually recompile my code. At least I hope that's the case. Let's see what happens. Oh, okay. Okay, cool. So we can reset. Yep. Let me. There we go. Okay, and let's see if it works. It should work the other way too. And who knows, maybe the reason why it's not showing any text now is because I think I left those lines commented out where that happens. Okay, we hit that, go into text mode, push a key and come back. Perfect. All right, cool. So that much is working at least. We can get rid of that. Let's try and just do one of these strings at a time. So let's try that. Let's see if we can print. There we go. And so we hit that, still no text. So I think what I'm going to do now is pull up one of my other favorite resources, which is the OSDev wiki, because they have a
a list of like, how to get started at with text mode and stuff. Here you go. I think we can do printing to screen in protected mode. We're not actually in protected mode, but it should basically be the same. Yeah, so we have B0, 0, whatever. Okay. Yeah, B8. Yeah, I don't know if that's whatever. Anyway. Yeah, so there's colors. Maybe I'm just using the wrong address here. Maybe that's what I'm doing wrong. Okay, so nothing is displayed, like, which is the problem I'm running into. We can set the video mode in within 10H, which is what we do. And yeah, this should just, yeah, I'm not sure what we're running into here, but okay, I'm gonna go back to printing to the screen. I guess there's a bias call I could use as well, but I don't know offhand what that one is, and I don't really want to go try and find it. So, oh, you know what it could be? It could be that we're printing black on black. So, let's try setting it to the color to the next whatever. Let's try also rating the color. That's what I'm trying to say. Um, Here we go. So what we oh man. So I think what we want to do is move AL, and then we want to say move AH. We can put the color in like that. And then instead of moving AL, we do AX. Let's try that. So I think what happened is that when you switch modes, the video memory, no, it doesn't matter. It doesn't work. The video memory gets cleared, and so we have to set the. Okay, let's try it the other way around. Let's try putting SI here, and because I never remember with Intel, it's which one of these ends up. I think it's because it's little Indian, so the low byte should go into the right spot. So anyway, yeah, the low byte should be into the first byte. No, that didn't work. Okay, so we want to go back to SI there, and AH can be 15. So we'll make it white again. DI 2. Yeah. I wonder. I think NASM's got some way to do like with respect to a different. So let me go over to my NASM thing here. It's like WRT. Yeah, Seg and WRT. I think is that what I want. Um, okay. No, I'm not sure the segments is really what I want. Like at any rate, I'm mixing the code and data segment together, so that shouldn't matter. We can try to let's try moving
let's move into AX, the code segment. Oops. And then let's move into the data segment AX, just to make sure they're the same. I don't think that's the problem I'm running into, but let's try it out. Okay, still in the text. Nope. Interesting. Hmm. Okay. Man, this is frustrating. It's like so close, this close to getting working, but what am I doing? Maybe okay. Let's look in the printing to the screen some more and see what yeah, so okay. So this is this attribute thing is the issue here. So 0 is considered black on black, 7 is light gray on black, which is the DOS default. 1F is white on blue, so that's going to make it look like the blue screen of death. That's how we do it. Let's see. Yeah, that's hmm. It's weird. Some of these have oh, I guess for monochrome it's in B000, and then if it's color text, maybe it's in B800. Yeah, I'm not sure what's going on. I know it's like something super simple, but yeah. Hmm. Oops. Man, I'm okay. Well, here's what I think I'm gonna do. I've been streaming for about 2 hours and 15 minutes or so right now, and that's uh kind of as long as I meant to be streaming for. So I think I'm gonna call it a night. You know, we started from scratch and we got most of a Pong game working, so I'm pretty okay with that. I think I'm gonna keep working on troubleshooting this, and when I figure it out, I'll do either another video update or um, you know, whatever. I'll do sort of a brief thing to let people know what the bug is. I'm sure it's simple, whatever it is, but I'm just not seeing it right now. And we'll pick up. I think I'm going to try and do this as like a weekly segment. So um, yeah, let's hopefully I'll see everyone next week, and we'll kind of keep continuing. Try to move towards probably either some more boot sector fun if that's what people want to see more of, or you know, start working into building a higher level language so you don't have to sit here and watch me type assembly language over and over and over again. Anyway, so that's what I've got. I will post the when I go to share this video, I will post the code that I worked on here on GitHub, so you'll be able to go and see that, and if you want to play around with it, you're welcome to. And you know, yeah, I'll post this on GitHub. I'll post this with some links and whatever else in there. So anyway, thanks everyone for watching, and we'll check back in next time and see
continue on. So thanks again, and I'll see you guys later.